Namaste everyone, welcome back to my channel Vision Tutorials/Han. In today's video, I will be discussing the pressure variation with the depth. I will be covering the concept of pressure variation with the depth, derivation with an experimental proof. Coming to the experiment. To start with the experiment, we need a bottle, balloons and clip. This is the experimental setup. I have drilled 3 holes at the different heights from the top to observe the water pressure variation at different depths. Now I have filled the bottle with the water. Later I will be releasing these balloons to see its behavior. Releasing the topmost balloon 1 as the pressure inside the balloon is more than the water pressure, the air gushes out of the balloon, which can be seen in the experiment. Now moving on to the releasing of balloon 2. The balloon 2 is at a higher depth than the balloon 1. Even here, air pressure inside the balloon is more than the water pressure, but air leaves the balloon at a slower rate compared to the previous release. Releasing the balloon 3, here we can see that no air leaks into the water and also water flows into the balloon as the water pressure is more than the air pressure inside the balloon. Here the water enters into the balloon as the water pressure is more than the air pressure inside the balloon. This shows that as the depth increases, the water pressure also increases. Let us see the science behind this experiment. Let us consider a container filled with water to a height capital H having density rho. Since the water surface is free to the atmosphere pressure acts on the top, which is PA. Consider a cylindrical water element inside the water container of height small h and area of cross section A. Since the water is at the rest, the horizontal forces acting on the water element is 0. However, there will be the vertical forces acting on the cylindrical water element. The vertical forces are F1 and F2. F1 is the downward force acting and F2 is the equivalent upward force. Other than the forces due to the mass of the water element, the weight force acts in the downward direction. By equating the forces in the vertical direction, we have the upward force F2 is equal to the downward force F1 plus the weight m into g. By sending F1 to left hand side, we have F2 minus F1 is equal to m into g. Since the density rho is equal to mass per unit volume, we have mass m is equal to rho density multiplied by volume. The volume of a cylindrical water element is area A multiplied by height of the water element. Thus, mass m is equal to density rho multiplied by area of cross section of the cylindrical water element A multiplied by height of the cylindrical water element h. By substituting the formula of mass into the equation F2 minus F1, we have F2 minus F1 is equal to density rho multiplied by area of cross section A into height of the cylindrical water element h multiplied by acceleration due to gravity g. Sending the area of cross section A to the left hand side, we have F2 minus F1 divided by A is equal to rho GH. Since pressure is equal to force per unit volume or unit area, thus F2 minus F1 divided by A is equal to pressure P2 minus P1. Thus, the change in pressure delta P is equal to rho GH. The rho is the density of the water, is constant, as well as acceleration due to gravity G is also constant. The pressure in a liquid varies only with the depth or height h. This is called as the gauge pressure. P2 is the absolute pressure, which includes the atmospheric pressure PA and the hydraulic pressure P1. Thank you. Keep your dreams alive at Vision Tutorials /Han. Please subscribe to my channel Vision Tutorials /Han.